the less the reason they essentially have to move. And again, this is what kind of creates the insulator. So what we're essentially doing is manipulating the semiconductor to kind of enact insulator type properties. Okay, and this is what creates a reverse bias, where now our depletion region, instead of just being here, is very small. Obviously this is substantial on the projector here, but understand this is thinner than a hair. Okay, where we've taken it, we've essentially blown it up to substantial size. And notice, please, that the holes don't actually move, right? Because they're not essentially real, right? They're kind of this this explanation on how when electrons move, there's a free space open for that we essentially create a hole or lack of an electron. But the holes don't actually move, right? They stay in their place, and that's kind of the rule, is to be the carrier. Okay, they are a transport, kind of a place to stop for the electrons in order for them to move. Okay, so now let's cover down on forward bias. Okay, so this is going to be a little bit easier to understand. So if I take forward bias, again, I'm taking the terminal of the battery and I'm connecting it to its proper terminals, and that's going to be on the P side, or the anode. I'm taking the positive battery terminal and I'm connecting it there. And then again, this is forward bias, and then I'll take the negative terminal and I'll go ahead and connect it to the N-type side, or the cathode, which in this case is on the right side. Okay, when I do that, I essentially flood the anode with more spaces for frogs to essentially get to, and then I give it a difference in potential, right? I add this electrical pressure, okay, as we know, which is voltage, okay, and I give the frogs, or the electrons, on the N-type side, and of course coming from the battery itself and voltage source and current source, to enough energy to bypass, right, to jump over this depletion region. Okay, and now what I can do is I can keep flooding this over and over, right? So the depletion region will stay small, okay, because the full atoms on either side are still essentially happy. Okay, so most of the work is actually being done on the side of the anode, okay, where this is the important part. And if we ever look into batteries, lithium-ion batteries and everything, you'll see that the anode plays a crucial part. Okay, and I'll kind of go back and I'll show you that again, where this is our voltage. We're kind of paying that toll to cross a bridge, okay, and we're giving it 0.7 volts at a minimum in order for it to cross. And anything above that is where you start tacking on your voltage. So understand, this is important to know if you're creating a circuit that requires multiple semiconductors. Okay, they each require, especially if you're using silicone type, about 0.7 volts. If you look at germanium, you're probably going to be looking at anywhere between 0.4, 0.5, so a slightly less requirement. So just keep that in mind. And I really hope that that this video kind of helped you out in understanding the concept between the PN junction and forward and reverse bias. And here's a small gift to kind of send everything home and tie everything back in. And this is showing forward bias. Notice that the positive terminal battery in forward bias is connected to the anode. The negative terminal battery is connected to the cathode. Okay, here we go.